So for some definitions, the more formal definitions are going to be in the boxes on the left. I'm going to talk about them more in layman's terms. So when we're talking about a global maximum or absolute maximum, you're talking about the highest point on the whole graph. Of course, you can do the same thing for a global or absolute minimum. One thing to make sure you realize is there's a difference between the maximum value, right? That's the y value of the function, versus where the value occurs. It occurs at x equals a. And you can also talk about the maximum point, which is, of course, the x, y together. So some definitions. You can also have some local or relative maximums and minimums. F has a global extrema at x equals a. So you can see on this graph in the lower right, you've got a global and local maximum. And, a point like that, that's a local maximum. It's not as high as the highest point, but it's high relative to its neighbors. And you can look at the same thing for the minimums. So a theorem, if f is defined on an open interval and you have a local extreme of f, then either f prime is 0 or f is not differentiable. Now remember, saying that f prime is 0 means that the slope of the tangent line is 0. So look at those 2 points. Those 2 tangent lines there, their slope is 0. That's where you're going to have a local maximum or minimum. Or the other thing that can happen is f is not differentiable today. There you're talking about something like an absolute value graph where you've got a corner. It's not differentiable there, but it's clearly a local minimum and an absolute or global minimum. So we care about points where the derivative is 0 or it's not differentiable, and we're going to call them critical numbers. The other points that we care about in that situation is going to be endpoints, because if you look at this graph here you have a local minimum and here you have a local and absolute maximum. Now honestly, some people don't call the endpoints local minimums and maximums because they don't have anything to one side to be a neighbor of, but we're not going to get that picky. The other thing that's important to realize is an extreme value of f can only occur at a critical number. Finding critical numbers are really important because that's going to tell you where to look. And at the same time, just because you have a critical number doesn't mean you have an x value for an extrema. So just something to be aware of. So let's look at an example. Find the local and absolute maximum values for this function. Let's go ahead and take the derivative of the function, right? We're going to try and find some critical numbers. When you take the derivative and set it equal to 0, you get 2 answers, the negative square root of 7 and positive square root of 7. Of course, that's this approximately that guy there is the negative 1, and approximately that guy there is the positive 1. These are the critical numbers, in addition to negative 4. So just from looking at the graph, we know what they are. Negative 4 is a local minimum. And again, some people don't call that a local minimum, but we can. X equals negative square root of 7. We have a local maximum right there. Positive square root of 7. That's both a local and global. Oops, not maximum. This is wrong. This should be a minimum. And there isn't a global maximum because the graph goes forever and ever up, so there's no highest point. So just restating that, we need to figure out what those minimums and maximums are. So I went ahead and plugged in the 3 critical numbers we have. We got some lovely numbers there. And so at this point right here, we know you have a minimum of 25, right? When you plug in negative 4, you get 25 at x equals negative 4. And there's a local maximum at x equals negative 7. And what is it? When you plug in negative square root of 7, you get this lovely number. And similarly, you do the square root of 7. And again, there's no global maximum. So example 2, let's go ahead and find the local and absolute maximum values for this function. Just looking at it, you know that you have just one local and absolute. And actually, this is a minimum. I've been having some problems, I guess, with my minimum and maximums. When we take the derivative of this and set it equal to 0, the only way that a fraction can be 0 is if the numerator is 0. So let's go ahead and solve that. X is 3/2. And when x is 3/2, we know that the y value is the natural log of 19/4. So that's what this point is right here. Now remember, there's other possible critical numbers where it's undefined, and it is possible that this is undefined if you can make that 0. But if you try solving that, you'll find it's a complex number with an I in it. So there are no other critical numbers for this function if you're dealing with real numbers. And there's a local and absolute minimum of the natural log of 19/4 at x equals 1.5, right? 1.5, 3/2, same thing. And just like the last problem, there are no local or absolute maximums for this problem. So example 3, let's look at this one. Looking at it quickly, it looks like there may not be a maximum. Let's go ahead and do the calculus. When I took the derivative, you're going to need the product rule, by the way, because you've got x times e to the negative 3x. When I take the derivative, a good way to solve when something like this equals 0 is to factor things out. Notice they both have an e to the negative 3x, so I factored that out. The only way for this to be 0 is if negative 3x plus 1 is 0, because this is always positive. And the only way for negative 3x plus 1 to be 0 is if x is 1/3. So there is a critical point. Let's go ahead and look at the graph a little closer. And you can see, as I zoomed in, I kind of am looking right in here somewhere. When you zoom in, you can see it. And there it is, x equals 1/3. That's going to give you a local and global maximum. Let's go ahead and plug that in. It looks like it's 1/3e. So the local and absolute maximum of 1/3e at x equals 1/3. Example 4. Find the local and absolute maximum values for this function. This time let's do it without the graph. Right? We've been using the graph to help us find if they're local maximums or minimums, to help us kind of know what we're looking for in the first place. But let's just do the calculus blind. So when we take the derivative, this one's kind of ugly because we have the quotient rule. The quotient rule is not my favorite, but we end up with this lovely equation. We're not going to have the same possibility in terms of maybe the denominator is 0, because this is already always positive. So all we really care about is where is the function of the derivative 0. So let's go ahead and solve the numerator equaling 0. And you actually get 3 answers, 0 and plus or minus the 4th root of 3. Now when we do finally look at the graph, you can kind of see what the graph looks like a little bit, but it's pretty darn short. So let's zoom in a bit, and you can see that the negative 4th root of 3 gives you a minimum. The positive 4th root of 3 gives you a maximum. And there's a question, maybe if we zoom in more at x equals 0, we might see there's a maximum or minimum there. But no matter how far you zoom in, I only did it a little bit here, but no matter how far you zoom in, you can see there's no maximum or minimums. We're actually going to learn in the future exact ways of determining if something is a maximum or minimum, because honestly, I still am not positive that x equals 0 is not a maximum or minimum point, because maybe if I zoom in close enough, I'll see something. But for now, we're just going to assume that zooming in is good enough and there is not a maximum or minimum there. So this is the example where you have a critical number, you have the derivative being 0, but you don't have a local or global extrema. So let's look at this problem with a clean sheet. We know we have these critical numbers. We know that 0 doesn't give us anything, so when we plug in our beautiful x values, we end up with some just as beautiful y values. And there's a local and absolute minimum of this lovely value here at this x value. And again, I know that because I can look at the graph. And we know it's an absolute maximum right there because I can look at the graph again. So another example, example 5. Let's look at this one. Looking at the graph, we can see that we probably have some issues here. Right there and there, you can pretty much guess that it's not going to be differentiable. And we also have some local and absolute minimums there, it looks like. Also, it looks like right there is a local maximum. Let's do the calculus. When we take the derivative, we end up with this function value there. And the only 0 is when x equals 0, because the only way for a fraction to be 0 is if the numerator is 0. But remember, we still have the 2 local and absolute minimums that from the graph, and that's where the derivative is undefined. That's where the 0 is going to be in the denominator, which of course is not allowed. You're never allowed to divide by 0. And that's how we get these critical numbers plus or minus radical 3. So we have two minimums that occur at the x's, x equals plus or minus radical 3, and the local maximum is at x equals 0. Now notice in this example I'm not actually finding the y values. That's because the question is asking us to find where they occur. They're not asking us to actually find what they are. So just something to be aware of when you're doing problems. Be careful about what the question asks for.